Okay. Good morning to everybody, and welcome to this new event in the series of seminars within the PhD program in aerospace engineering and science. And today is a pleasure for me to introduce to you this new seminar that will be held by Tommaso Sgobba. As I like to mention every time I can introduce another seminars of this series, it has been a very good opportunity for all of us, the possibility of listening speakers coming from different fields, from university, from companies, from agencies working in the aerospace sector. I believe that it has been a good opportunity for our PhD students, but also for all the people working in our region, in Italy, in this field, because it is clear for all of us that many opportunities can come from the aerospace field. In particular, today we are talking about a very interesting field. Everybody who has got the opportunity of working in the field of designing components or parts in the aerospace sectors has had the opportunity to understand how important is for engineers to understand and apply standards. And the consequences could be also catastrophic in case of something during the interpretation, during the application of the standards goes wrong. So I strongly believe that the today's speech will be of real inspiration for all of our PhD students, but also for all the engineers that will have the opportunity to follow this speech. I do not want to waste much more of your time. I give the floor to Professor Vito Albino, who will introduce our speaker, Tommaso Sgobba. Just another couple of words. Thank you, really, Tommaso, for your kind availability for being today with us in a virtual way, but at Politecnico di Bari. Hopefully, we will have soon the opportunity of hosting you in person here in Bari. Thank you again.
Thank you. Thank you.
Okay. Thank you, Professor Cupertino, and thanks for the invitation to be moderator for one of the inspiring speeches in this PhD program in aerospace science and engineering. Today we have a special guest speaker with us, and I have the great pleasure to moderate this event. Today we have Tommaso Sgobba. He is Executive Director and Board Secretary of the International Association for the Advancement of Space Safety. I'm honored to present Dr. Sgobba. He has a very outstanding curriculum vitae, and then have to make a selection to be, of course, short as this seminar required. And of course, as I mentioned, Dr. Sgobba is Executive Director of the International Association for the Advancement of Space Safety, and he has been the first president of this association in a period of 2005 to 2013. Dr. Sgobba holds a Master of Science in Aeronautical Engineering, so it's an engineer from the Politecnico of Turin, And there he was also professor of space system safety. He joined then the European Space Agency in 1989 after 13 years spent in the aeronautical industry. He has been responsible for flight safety at the European Space Agency, including human-rated systems, spacecraft re-entries, space debris, and planetary protection. Initially, he supported during this period in ESA the developments of the Ariane 5 launcher, several Earth observation meteorological satellites, and the early phase of the Hermes space plane. I didn't know about this, when I got this information, I wish to do some question to Dr. Sgobba. Of course, he is a very expert in product assurance and safety, and he has been involved in several European manned missions on shuttle, on Mir Station, and on the International Space Station. He chaired for 10 years the ESA International Space Station Payload Safety Review Panel. So a great experience is with us. He has also published several articles, books, as well as he has received NASA recognition for his contribution, for his outstanding contribution to the International Space Station and the prestigious NASA Spaceflight Awareness Award in 2007. So Dr. Sgobba is a person where theoretical knowledge and practical experience are joined for what is a crucial activity for space exploration, that means to enhance safety. I wish to spend a few words also about the International Association for the Advancement of Space Safety. That is a really important association established in 2004 in the Netherlands. It's a non-profit organization, and with a mission to improve space system safety. And I wish to mention that the association also pursued the safeguarding and sustainability of the on-orbit environment to allow unpeded access to space for future generations. And maybe this association can play an important role, like the one played by ICAO, the International Civil Association Organization, in the next future for space coordination and space safety. So the title of the talk today is B737 MAX and the crash of the regulatory system. Most of you know very well the Boeing B737 MAX. It's an airplane that unfortunately is now famous for two accidents, one in 2018 in a domestic flight in Indonesia, and the other one in 2019. It was an Ethiopian airline flight from Addis Ababa to Nairobi. And then the talk will show and compare different approaches to safety, in particular the compliance approach, prescriptive approach, and the performance-based approach. And organizational aspects and risk have to be considered when approach selection is made, or when the evolution from one approach to another approach is ongoing. And finally, I wish to tell that another topic from my point of view is really relevant, and I'm sure Dr. Sgobba will tell us about. It is a problem how failures and accidents drive the knowledge development of a safety system. This is true for technology, but in particular for safety system. And in a world of increasing complexity, think about global space safety, for instance, what we learn from failure and accidents continuously help us to enhance procedures and products. But now I wish to be silent and to leave the virtual floor to Tommaso for his speech. Please, Dr. Sgobba.
Okay. First of all, thank you very much for this invitation. For me, it's a double pleasure to be talking today at this seminar organized by the Politecnico di Bari, because Bari is my hometown, which I left in any case 50 years ago. So it's quite a time that, I am not there, at least not permanently there. As was mentioned, I am an aeronautical engineer. I started my career as an aeronautical engineer, then I moved to space, and space was for 24 years my profession. When I was studying at the Politecnico of Turin, aeronautical engineering, I had as professor Gabrielli. Gabrielli was one of the last, I would say, charismatic airplane designer in Italy. He had a long story of, designing successes and operation. And Professor Gabrielli used to say that every good airplane is smeared with blood, is covered with blood. I don't believe that nowadays any large company like Airbus or Boeing takes pride about accident, okay? But the idea, which has been very much embedded since the beginning in aviation, has been we do our best, we learn as we go, and we learn from accidents. But at the certain point in time, and now I am talking about nuclear, for example, or space, we start developing systems which either because of the high criticality or because of the high cost are not there to be, a repeat learning lesson. So you have to be right from the beginning. Nuclear and space station. You cannot just build several space stations and learning as you do. So for systems like space station, etc., and nuclear, we use a risk-based design. Now, we have built the International Space Station only through risk-based design, which is something that truly is not generally done in aviation. And when I looked after several years in space into the business of aviation, in particular this accident, then I realized quite immediately that was some fundamental mistake, I would say. I don't want to sound arrogant, but unfortunately, the things are so evident, when you look a little bit carefully, that cannot be missed. In my view, this accident of the B-737 will be a divide of two epochs. As it happens once with the Comet aircraft, in the future, there will be a time before the B-737 MAX and a time afterwards. And this is in relation to the regulatory system. Next slide, please. So what I will present to you is tell you is that a number of industry, traditional industry, shipbuilding, aviation, are basically doing what has been done for nuclear and what has been done for space, transitioning from prescriptive requirements to performance requirement. Now, we should not be betrayed by the terms, because prescribe and require are synonym. Okay, so why we say prescribe and require? Because this term refers specifically to the prescription of design solution. So when we say prescriptive requirement, we say that it is an approach by which depending on the type, helicopter, small airplane, large airplane, etc., landing gear, subsystem by subsystem, there are specific rules to be followed for the design. These are prescriptive requirements. Performance requirement is what by necessity has been done in those other industry, in which not having available or not wanted to give prescriptive requirement because truly were not available, goals given were basic in terms of acceptable risk level. Okay, this is what now is happening in aviation. Transition ongoing. FAA in US already is transition, so-called generation, with the airplanes, and this transition of large airplanes. The point is that truly aviation has already had quite a substantial experience in the field of performance-based requirement. And this is basically what I will explain to you, and will explain to you that it is due to these specific needs that today talking about the B737 accident. Next one, please. Next one, please. Yes, this is just of what I said: prescriptive standard, specific design requirement, performance standard, the outcome, the safety level. Next one. There are advantages with prescriptive, because prescriptive are very clear, simple, straightforward. You have just to follow the code and implement them. There is no room for interpretation, and you do it as required. Next one. Next one. No, please. Sorry.
There is a delay. Sorry.
Yeah. So what are the disadvantages of prescriptive standard? What you see in the picture on the side is the Titanic. The Titanic sank in 1912, and there were 1,500 people losing their life because there were no sufficient lifeboats on board. There were no sufficient lifeboats on board because the requirements applicable at the time the Titanic was built were requiring only 16 lifeboats for any ship with a tonnage above 10,000 tons. The requirement had been written just a few years before the disaster, but in these few years there was an evolution of the shipbuilding capability, etc., that the 10,000 tonnage was easily overcome, and then at the time of the Titanic, it was 46,000. Now, the designer of the Titanic, they knew perfectly well that the lifeboats were not needed. And they discussed this point. They said, why we don't put more lifeboats? And the point was, the Titanic is unsinkable. Therefore, why we want to bother with lifeboats? What does the code says? The code says 16 lifeboats. I believe that they put a few more, and that's it. And this is what happened. So the disadvantages of descriptive requirement is that they cannot keep the pace with the evolution of the technology. And sometime, or in many times, they mandate solutions that are not necessarily cost efficient. Prescriptive requirements are reactive. They are identified after the disaster, and so on. Please, next. So the approach that we are talking about is an approach by which, by experience, detailed safety requirement to be used during the construction, detailed safety procedure, and detailed verification, testing, analysis, inspection of those requirements are identified. Therefore, the role of the regulatory authority is the one of providing the standard and basically to verify by inspection and testing that the standard is followed. What does it mean? It means that you don't need much skill into the verification, because truly the investment in skill and competence has been in writing the standard. So for the inspection, you go there and you count how many lifeboats there are on board. 16, you are okay. You are according to the code. Next slide, please. Performance standard is a different beast. Is oriented to a goal, and this goal is a safety goal. This is done basically by prescribing either a quantitative safety target or prescribing a qualitative safety target. You must be two-fault tolerant, for example. This is not a design rule. This is a goal, because then to implement this two-fault tolerance, there is a lot of study and understanding of the way the system works to make this a reality. There is therefore requirements that are quantitative and must be compared with prediction, and requirements which are quantitative and can be compared with measurement, like the amount of contaminants into the air. Some requirements are objectively verifiable, like the one that can be measured. Other, like prediction, we will see later, are truly impossible to demonstrate. Next, please. What are the limits of the performance standard? The limits is that performance standard, although they give a lot of flexibility to the designer, they are a little bit vague. They are imprecise. So they need to be interpreted, and the interpretation eventually needs someone to confirm that interpretation is okay. So you need, in dealing with a performance requirement, a lot of skills, and in particular, you need a lot of skills when you have to validate a design, because the design that is offered to you is the opinion of the developer about what meets the objective. But you need, skills, specific skills to evaluate the design. Next one, please. That is what we do on the space station, in the nuclear field. And basically, we move from targets, performance target. And here I have to make a small, let's say, clarification. Is not that prescriptive requirements are completely ignored and are not used at the system level, but they continue very often to play an important level of the batteries, vessels. For these items, there are descriptions how to design it, how to manufacture it, how to qualify it, which have an enormous value. So the reality is that we have a mixture of performance requirement and prescriptive requirement, performance system, prescriptive requirement, lower level, etc. And an hazard analysis is done. And as a result of this hazard analysis, the detailed safety requirement and solution, procedure and application are identified. This is the risk time. The case is basically the presentation of the result of the analysis in an independent panel, which basically validates that the designs are true meeting in the rules. Next one. The independent safety I mentioned, the panel must be independent and be multidisciplinary and must have competences equal or better than the one of the designer. Next one. So, having done this foreword, let's say, this introduction, let's talk about B737 MAX, the MCAS. Next one. So, when we look today at the appearance of an airplane, okay, it does not look very much different from what we had 50 years ago in 1966 and so on. So externally, the airplane looks still the same, but internally, out of the view of the passenger, there has been I would say, a dramatic revolution. In these days, there is a video circulating which shows what is beneath the floor of the cockpit of the Airbus 350. What is there is a data center with servers, one on top of the other, with racks, etc. Is a data center. So there has been a revolution in aviation with the introduction of computer. Airbus has been leading this revolution. Boeing has followed, but in certain cases, like the B737, truly has mixed the two approaches, mechanical connection together with, let's say, autopilot, auto throttle, and similar, in a formula that theoretical should be even better than the purely fly-by-wire and remote control used by other manufacturers. So there has been a revolution. What happened with the rules? Because the rules of aviation has been traditionally prescriptive requirement. You build in this way your system. When you introduce a computer system, you don't have truly rules that you can impose. Next one. First of all, what is the accident? What happened to B737 MAX? There is on every airplane, and this is the top picture on the right side, there is a small sensor which is called AOA, angle of attack, and this sensor basically is a sort of small flag that orients with the flow of air. There is an optical reader behind, quite a simple mechanism, and therefore the pilot in the cabin, they know what is the relative position of the airplane with reference to the airstream, okay? This information is very important because there is a criticality of the angle of attack related to the flight capability of an airplane, by which at high angle of attack you can incur in a so-called stall. The stall is, simply said, the loss of lift of the wing, which is for a large airplane like B-737 unrecoverable. Therefore, every airplane has this sensor. Usually there are two sensors on each side of the airplane. In the case of the B-737, the B-737 was an old overall architecture of the airplane of the 60s, first flying 66. The Boeing 737 was designed to be very low with reference to the ground, okay? It is very low. The landing gear is very short. The reason for having this choice for the B-737 was that they wanted to offer the B-737 to airlines to be used also on airport with limited ground infrastructure and even unprepared runways. Therefore, by landing in this small airport, you don't need someone from outside to come there with stairs, but B-737 has its own stairs, which are unfolded just beneath the door, and the passenger can leave the airplane without any external aid. To do this, the airplane was very low. At that time, the time of the 60s, the airplane had had a jet engine, but with a very compact and limited diameter. With the passing of time, the engine started growing because of the use of the so-called bypass engine. And first, this was accommodated by the B-737 with a relocation of certain items of the engine, such that if you see most of the B-737, not the MAX version, in flight, you see that they have a strange shape that is flat on the lower side of the nacelle. When the B-737 MAX came, the engine diameter was even larger and the engine was even heavier. The solution with a low aircraft was to move the engine up and in front of the airplane. And this changed basically the initial configuration of the COG of the airplane, center of gravity, and also aerodynamically. And this caused for the airplane in certain conditions to have a tendency to pitch up, to move the nose up. So what they thought at Boeing, okay, nowadays the use of software to give agility, so-called to fighters, etc., is common. So airplanes are no longer necessarily stable by, let's say, mechanical design, mechanical configuration. We can make the airplane stable by software, okay? So the MICAS was introduced that working in the background of the pilot and even unknown to the pilot on board the B-737 MAX didn't know at the time of the accident there was a system installed called MICAS, So in the background, this system was making sure that if whatever reason, the angle of attack was being exceeded, then the nose was put down. And not once, repeatedly. And this basically was the cause of the accident. Two accidents. Next slide. We covered this. Yes. Here, what you see in this image is basically the way that the MICAS works. Basically, there is an actuator that moves the rear stabilizer of the airplane, which is what is normally called the trimming of the configuration. And basically, the MCAS operates on this motor, electrical motor, moving the rear part of the airplane, so that while the pilot commands the elevator, that is the small part behind the stabilizer, to climb, the stabilizer would rotate such to put the nose down, and therefore counteracting the action of the pilot. Because of this, 346 people were killed. Next slide. Automation in aviation has changed the airplanes and has changed the pilots. Nowadays, the pilots are no longer, let's say, controlling the plane physically. They are monitoring the system on board, which truly fly the system. And it is notoriously that when there is something going wrong, the automatic part disconnect, and the pilot very often are completely taken by surprise. They don't understand what is happening. They are slow in reacting. This is what happened, but still the requirements in aviation are prescriptive requirement, which look for inspection and testing as a way to verify compliance, and the pilot is trained according to procedure. So we have the pilot, the machine as a separate entity. Next one. To solve the issue about how to deal with this new computer-based system, the idea of equivalent safety was introduced. Basically, the idea was the following. You first do an analysis, a functional analysis of the system that you are going to implement now by means of a computer. You determine what happens if that function fails, and then you have to comply with certain performance-based requirements, which are the objective of your design. So if the function is defined to be catastrophic because the failure of the function brings the airplane to a catastrophe, then it is required that your system must be as reliable as able to have 10 minus 9 flying hours without a failure. Plus, if it is catastrophic, your system must be fail-safe. This is the top level, catastrophic. Then there is hazardous and major for lower level criticality. So the idea was, okay, we give you now no more rules, we give you objective, and these objective are reliability objective, plus in one case catastrophic, a qualitative rule that is fail-safe. How this number were generated, next one. This number were generated with a philosophical logic, which in itself does not look very bad. And the philosophy was, okay, we take, this is what the regulators did, we take the number of accidents in the period between 1970 and 1980. We look how many failures, how many accidents were caused by system failures. And then we consider that there are on board of an airplane 100 critical systems, and this is y10-9. Okay, so it was an artifice like this that bring, to determine the 10-9. Next one. Therefore, demonstrating compliance with the requirement became a demonstration of so-called equivalent safety. So doing a functional criticality analysis, what happens is if this function fails, and then making a reliability analysis to show that you had the reliability as minimum required by the norms. Next one. What was that they did for the MICAS? Now, MICAS has caused, in the matter of 3-4 months, 2 catastrophic accidents. But the MICAS was, the function of the MICAS was classified as major, 2 levels below catastrophic. Why it was classified major? Because Boeing rationale was when the pilot sees that the stabilizer is moving by itself without being commanded, there is a procedure which is called memory items that he will do, and with this procedure he will gain full control of the airplane. What is a memory item? A memory item is a special kind of procedure used by pilots, which is so time critical that you have no time to look into the checklist. When you have a problem on board an airplane, the pilots will look into the checklist about that problem, how to solve it. You have no time to do the checklist. You have to memorize the checklist so that between you and the co-pilot, you do by memory the procedure for what is called a stabilizer runaway. So it's a time critical procedure. Now, what is the mistake? The mistake is to consider that what we in space and in other industry call an operational hazard control becomes a way to reduce the severity of the function. This is a logical mistake because it is the severity of the consequences of losing a function that drives the hazard controls that you need to have on board, and not the other way around, okay? It's like saying that losing the function of a parachute is catastrophic, therefore I use 2 parachutes, but because I use 2 parachutes, I will not have a catastrophe, therefore I can do with only 1 parachute. This is the rationale that they did. They went the other way around. Next item. In space and other industry in which we use hazard-based design, there are a so-called precedents in the reduction of the hazard. So first, you eliminate, if you can, the hazard. Generally, if the hazard is a functional hazard, it cannot be eliminated without eliminating the function. So in this case, would not apply. Or you use a safety device. A safety device could be a redundancy, a switch, things like this. At lower level of preferences, there is a warning device that basically tells to the operator there is something wrong, you have to do something about this, and or a procedure and the training. Basically, at Boeing, they took a procedure that was there, the memory item that was there for other failure, and they considered this to be the automatic reaction of the pilots. So they used an hazard control to decrease the criticality classification of the function. Let's take a quick look to what they did after the accident, because this kind of scheme is eventually also the one that they followed. And what they did was, in the case of the MICAS, the sensor, only one sensor was connected to the system. They connected both sensors. They put a warning to the pilot when the two sensors were disagreeing, and they have nowadays specific simulation and the training procedure for the pilot. So they did what normally they should have done before the accident. Next one, please. Is this all? So there was just a mistake that, you know, the last straw that made the camel collapse. This was just one of a kind, etc. No, it is all the system that does not work. So the overall approach is flawed, and there is another problem of the strength of the regulatory of organization. Let's go on. Next one, please. Where is the flow of the approach? We have seen, first of all, the fact that they have modified the classification of a function criticality based on an hazard control that they would put in place. But the fundamental mistake is that the risk approach used in aviation, and risk equal probability of something going wrong with reference to the consequences, they concentrated on hardware failure. So the system unity, the system is the hardware, the software, and the pilot, nowadays called liveware. So this is the system. They had broken the unity of the system by basically making coinciding the risk with the probability of hardware failure and not the probability of system failure. The software, it is impossible truly to attach a probabilistic value to a software, as well as it's very difficult to attach a probabilistic value to the failure of the human. This is why when you quantify the risk, it's almost impossible that you have a means to quantify, beside hardware, in which we may be quite good, also the reliability of the software and reliability of the human. But what they did in aviation was to separate the issue. So the hardware is one thing, the software, you just build the software in accordance to strict procedure that may be more or less strict depending on the criticality of the function, and then you train the pilot. But nowadays, the more there is software, the more there is intelligence, let's say, on board, and more the three things interact, play together. So this is the fundamental flow of the current approach to risk-based design in aviation. Next one. So basically, the risk-based design shift from a risk evaluation to a reliability analysis. But there is something even additional and serious. FAA has basically delegated since a number of years the certification to the companies. Nowadays, in United States, 94% of the certification activities for a new airplane are done by the company itself in a sort of self-certification. This self-certification was in itself an evolution. They started at FAA already in the 20s and 40s, etc., delegating certain tasks that were inspection tasks from FAA to the maintenance people, and then to the manufacturing people, and then to the designer people. But these were specific delegation on specific task to specific people with competences. To make an example, I worked on the Boeing 767 program, and we produced, I was a structural engineer, and we produced a lot of structural analysis. Now, in Boeing, there was a guy that was not part of the Boeing program office, and he was the guy who would go through the analysis and basically stamp the analysis as being done in accordance to the FAA rules. But one thing is to inspect an analysis, to inspect an hardware, and one thing is to put together the entire story of why a certain function is safe. Here, on one side is no more the single person that plays a role, but it is a team. But in the delegation that NASA has done, starting with FAA has done, starting initially with individual and later delegating the entire package to industry, still the tasks are segmented. You know, there is no something like a team approach. Just to give you an idea, at Boeing, to certify, to make certification activities, there is something like an office of 50 people from FAA, and there are 1,500 engineers from Boeing, which, although not full-time, work for FAA as certification support. Okay, so basically, most of the certification is done by the company itself. And when things have been, you know, a little bit looked into detail, it came out that there were, you know, some influences. So the independence. Therefore, the system is also flawed from the point of view of the regulatory oversight, because the oversight is still fragmented, is not made by multidisciplinary teams, and it is mostly delegated to the company itself with a lack of independence. Next one, please. What the association IAAS is doing is to recommend the creation of an intermediate organization between industry and regulators. A safety institute is the name that we can use to identify the role, that would have the technical capabilities on demand with not permanent staff, because if you create a permanent staff, you create a bureaucracy. And in this staff with task-oriented activity ad hoc, there would be people from industry, perhaps from the manufacturer itself, from the regulators, from academy, from other branches, okay? And they would take an approach that is a multidisciplinary approach to, you know, certifying a system. This is not an invention. Something like this was already created after the 3 Mile Island accident of '79, a nuclear power plant, was created the INPO, Institute of Power Operation. There was another institute with the same kind of scope created after the Deepwater Horizon oil rig disaster in the Gulf of Mexico of 2010, which is called Center of Offshore Safety. So the proposal that we are doing is to create intermediary institute. Is this a dream? Not at all, because 2 months ago, the Aerospace Corporation, which is the most, let's say, skilled research center, aerospace research center in US, as the size of a space agency and the funds to go with it, has established internally a Space Safety Institute for space activity, and will start offering this service in the near future. Next one. Conclusion. Current airworthiness standards are either antiquated, prescriptive oriented, or inadequate performance, but reliability based. This needs to be changed. Currently, it is considered that accidents arise from hardware, from failures of hardware, software, human, considered separately. This needs to be integrated. And the safety certification process has become progressively less effective because of lack of skills and resources at the regulator. Next one. So this is the afterword. What is shown there is a report that has been issued in September by a committee of the US House of Representatives. So this is the US Congress House of the Representatives. This is a report of the Transportation and Infrastructure Committee. And this report says, if an airplane is certified as safe by FAA and still today considered fully in line with the certification requirement, so there is nothing that can be, said against Boeing in terms of complying with the rule, then there is something of a big problems with the rules. And they made the honor in this report to mention my name and the publication that I did explaining what I have told you today. So this ends my a little bit longer presentation, and this is why I believe that we are at the beginning a new epoch in aviation safety. Thank you very much for your attention.
Can you hear me?
Yes.
Okay. Thank you, Dr. Sgobba, for your presentation. I think that several issues have been underscored in starting from your words, and I think that young students, PhD students, can learn more from this speech than from the reading of a book, because you are referring to an extraordinary experience, and as the final committee report mentioned, of course, we have to take time to reflect about the accidents and the problems that are emerging. And I wish to start the question section with not a comment, but with a very simple question to you. Which has been the role of technology progress? Because you said it's a milestone in the progress of safety. I mean, the accident of Boeing 737 MAX is a kind of milestone in the progress of safety methodology. But what is now the role of technology progress? I'm thinking about artificial intelligence, and then what does it mean to have artificial intelligence applications on board? And what about the increasing rate of technology change? So how we have to deal with this new feature of technology progress? So this is just a question to start, but of course, if there are other questions, I'll be very happy to have the opportunity to discuss about them.
Yeah, I mean, the question is absolutely interesting, I would say, and I have a little bit my theory. And my theory is the following. The technological progress is wonderful. It's something that truly inspired us, etc. But with this technological progress, it comes to a large extent an inadequacy of the organization, large organization, complex organization. There is this book that has been written already some years ago, which is titled Normal Accident. Basically, it tells you that the more sophisticated the system become, the more they are integrated, the more the organization risks to fail. This is something, that normally we observe when comparing Europe and US. In Europe, we tend to have a wider scope of knowledge. In US, they have a little bit the silo approach. They go very much in the expertise in a specific field. So this means that putting together now all this knowledge and making sure that it's properly integrated becomes a problem, an organizational problem. Okay, system engineers. One of the answers to this accident has been FAA need more system engineer, but system engineer is an orchestra director. Okay, is able to do something if there is the orchestra, but alone he has nothing to play. Therefore, to conclude, technological progress is incredible, is very good, it's always very good, but since the time of the fire invention, the invention of the wheel, every technological process has driven a type of accident, electricity, and all the rest. So we need to have organizational means. And here, when I say organizational means, I refer also to a technological organization means. So developed a profile of engineer, for example, that can truly help in the integration of the knowledge for not only the purpose of optimization, which normally is at the basis of many engineering problems, but also for the purpose of, safety and environment protection, because these are other pillars, important pillars.
Okay, thank you so much. Professor Tullio, if you want to...
Yes, Vito, there is a question by Maria Cinefra.
Oh, thank you. Please.
Good morning. Thanks for your presentation. Do you hear me?
Yes, please.
Okay. So I am Maria Cinefra. I work in the field of aerospace structures, and I have a curiosity about the use of composites. If you know any details about the updating of safety regulations regarding the use of composites, since I work with the modeling of composite structures. Thank you.
Thanks very much for the question. I've been working you know, I would say quite a lot on composite, because when I was quality assurance manager for the plant where the flight control of 767 were developed, these were the largest composite structure of the time. And so we had to know a little bit about design and all the rest. But truly, there are things that are appearing now. I don't truly know how they are dealing with it, but you know better than me that damages to composite material is invisible. Okay, so what happens if during a flight you have so bad weather, hail? Perhaps you should avoid this kind of situation, because for other reason you don't fly inside a weather. But even if you are standing on the tarmac of an airport and you get hail, what happens to a composite structure? So for me, this is the major question mark technologically. The second is that we don't have yet probably a long experience in the field, and you know, we don't know really what the exposure of structure, you know, to many years of cycling, etc., means. Although, you know, they should ideally be in a much better position than the metallic material. So my question is, basically, I don't know the detail. I don't know the, you know, regulatory impact, but I can guess that this is an area that will more and more attention in the future. It's a bit hidden. Yeah.
Thank you. Thank you. It was what I expected.
Thanks a lot.
Thanks, Tommaso. I had a question, Vito, but I see that it's very similar to the one that Marica Patronelli wants to ask. So, Marica, you can activate your microphone and ask your question.
Hello to everyone. I'm Marica Patronelli, a PhD student. I work in the field of experimental mechanics, and I have a little experience with the regulation because my PhD is in collaboration with a small company, Black Shape Aircraft. So I faced with the CS23. And first of all, congratulations for your presentation. I read your article a few months ago, and it was very interesting. So my question is, in these catastrophic events, how much weight has the competition with other companies? And will the new intermediate organization be free from a pressure from an economic point of view?
Unfortunately, the competition plays an important role, as played an important role also in this accident, because Boeing in particular was running to deliver a product that could be, let's say, a competitor for the new Airbus A320neo. But there is something more, and this something more is when I was working on the Boeing 767, the people I knew from Boeing had been working on the 707, the first jet aircraft of Boeing. Engineering was the king. to become the president of Boeing, you had to be an engineer. Afterward, things have started to change. Nowadays, Boeing management is very much, let's say, financially oriented to provide results, to provide dividends for the shareholders, etc. And this is considered not a good result of the. So more than a competition is the excessive drive toward profit that may have hurt Boeing and may hurting other companies.
Yeah. Okay, thank you.
Yeah.
Okay, there are no more questions. So if I can, I have a last one, just a curiosity. In describing a complex system like an airplane, considering all the point of views, is there any role for uncertainty quantification of mechanics, software, human being? So when you evaluate the risk, how you manage the uncertainty of this complex system?
Very, very difficult question. When we deal with risk on the space station, I worked for 20 years on the space station. I personally chaired something like 800 safety review. The moment in which a developer says the word probable is out of the meeting, is finished the meeting. Okay. This may seem excessive, but in the world of risk management, quantitative quantification of the risk is not considered a viable approach, and therefore we tend to be a little bit perhaps excessive, but deterministic. You have the hazard, you have to do this. But the hazard, I mean, is very low probability. It's that we don't care about probability. There is the possibility, the credibility is what we use, which is a little bit of an equivocal term, because, for example, we say that the explosion of a pressure vessel that has been qualified and tested according to the norm of AIAA or ANSI norms is not credible. So over there is an amount of autocracy, if you want. But nevertheless, I tend not to believe that quantification and uncertainty should play a role in deciding the way to go. I may be a little bit old-fashioned, etc., but you know, when the Apollo system was developed at NASA, the Apollo capsule, okay, was a new capsule set, but the rocket, the Saturn rocket, was the first brand new rocket being designed by NASA for space, because the previous rocket, the Atlas, the Titan, the Redstone, used on Mercury and the Gemini capsule, they were all adapted military rocket, which had been already launched in one case, the case of the Atlas, before it being used to launch Glenn in space, had been already, let's say, operated 100 times. Okay, And so when the Saturn V was developed, there were two schools. One was the reliability school, and the other was the von Braun school. And the reliability schools was saying, okay, you take a reliability, you apportion the reliability to various subsystems, you go down to component level, then you test the reliability of a component, then you reassemble all the figure, and this is the reliability of your system. Von Braun said, basically, bullshit. You look carefully in the design. You try to understand if the design is sound. If it is simple, because if it is a complex design, then it can fail. You have independent assessment. You know, you have expert. You look into it, etc., etc. Eventually, this was the way ahead. At NASA, reliability analysis are still done, but they are considered a tool to compare the design, not as representing the true nature of the system. If you want to compare 2-3 design solutions, then you make a reliability analysis and you get a feeling about being on the right way, etc. So I am very much very distant follower of von Braun, although there is an ocean that divides us culturally, etc.
Tommaso, thank you. So Vito, I think that I can thank Tommaso for his inspiring talk. Thanks, Tommaso, for your effort in clarifying and informing us on the problem of licensing and certification. Thanks for your time, and thanks Vito, for moderating the event. Vito, I don't know if you want to make your final...
Just say again, thanks, and next time we expect you in Apulia and in Bari or Taranto.
Thank you so much for the invitation. Thank you.
Thank you. Thanks a lot, Tommaso. Thanks everybody for participating.
Bye-bye.
See you soon.
Bye.